I'm Adam from RFOXiA, from our real lab. Today we're answering why GNSS modules that work perfectly in open fields produce coordinates that are genuinely wrong in cities, forests, and anywhere signals get complicated. Enjoy our new soundtrack at the end of the video. Let me describe what your GNSS receiver is actually trying to do, because most of the confusion about urban positioning comes from not understanding the geometry the system depends on. A GNSS fix requires your receiver to calculate its distance from at least 4 satellites simultaneously. It does this by measuring the time it takes for a signal to travel from each satellite to your antenna. The math is simple. Signal travel time multiplied by the speed of light equals distance. Solve 4 of those equations simultaneously and you get latitude, longitude, altitude, and a time correction. That is the entire system. The problem is that every part of this calculation assumes the signal traveled in a straight line from satellite to antenna. In open sky, that assumption is correct. In a city, it is almost never correct. When a satellite signal arrives at a city block, it does not only arrive directly, it arrives directly, and it also reflects off the glass face of the building to your left, and off the steel cladding of the tower behind you, and off the wet pavement, and off the roof of the car 3 meters away. Your antenna receives all of these copies of the same signal, the direct path and every reflected path, arriving at slightly different times because they traveled slightly different distances. Your receiver cannot tell which copy is the real one. It averages them, or it locks onto the strongest one, which is sometimes the reflected copy and not the direct path. Either way, the time measurement is wrong. And if the time measurement is wrong, the distance calculation is wrong. And if the distance calculation is wrong, your coordinate is wrong. That is multipath interference. It is the primary reason GNSS fails in dense urban environments. The error magnitude depends on the geometry of the reflections. In a narrow street canyon with tall glass towers on both sides, you can see position errors of 10 to 50 meters from multipath alone on a clear sky day with a good satellite count. The sky is not the problem, the city geometry is the problem. Now add the second issue. When you are inside an urban canyon, you cannot see the full hemisphere of sky. You can see a narrow strip directly overhead. Satellites at low elevation angles, which are geometrically the most useful for horizontal position accuracy, are blocked by buildings. The satellites you can see are mostly directly overhead, which gives you excellent vertical position information and poor horizontal position information. This is called geometric dilution of precision, or GDOP. A poor GDOP means your position solution is mathematically unstable. Small errors in individual satellite measurements produce large errors in the final coordinate. A cheap module with a single constellation, GPS only for example, might only see 3 satellites through that narrow sky strip. 3 satellites is the minimum for a 2-dimensional fix. There is no redundancy, no error rejection. Every noise source goes directly into your position output. A multi-constellation receiver, one that sees GPS, Galileo, GLONASS, and Beidou simultaneously, has access to 3 to 4 times as many satellites. Even through a narrow urban sky corridor, you typically maintain 8 to 12 visible satellites instead of 2 or 3. More satellites means better geometry. Better geometry means the math is more stable. More stable math means errors from individual multipath reflections are diluted across a larger solution set rather than dominating it. Now move from the city to a dense forest. The failure mode is different, but the result is similar. Tree canopy does not reflect signals the way glass does. It absorbs and scatters them. A thick forest canopy attenuates L-band satellite signals by 6 to 15 decibels depending on canopy density and moisture content. Wet leaves are significantly worse than dry ones because water is an excellent microwave absorber. A signal that started at the satellite with more than enough power to be decoded arrives at your antenna below the sensitivity threshold of your receiver. The satellite simply disappears from your fix. Your satellite count drops, your geometry collapses, your position error grows. And then there is the third environment, anywhere with dense radio frequency noise, industrial areas near power lines, near other wireless infrastructure. GNSS signals are extraordinarily weak by the time they reach ground level, around minus 130 dBm. Almost any source of electromagnetic interference can mask or corrupt them. A cheap module with no RF filtering is equally sensitive to satellite signals and to noise. A module with a proper RF microstrip bandpass filter rejects energy outside the GNSS frequency band before it reaches the receiver chip. This is not a minor improvement. In a noisy environment, the difference between a filtered and unfiltered front end can be the difference between a working fix and no fix at all. The Multinav Pro Plus addresses all 3 of these failure modes. the multi-constellation engine, GPS, Galileo, GLONASS, and Beidou simultaneously maximizes your satellite count regardless of sky view. More satellites mean better geometry in urban canyons and more redundancy in forest environments where satellites fade in and out through gaps in the canopy. The RF microstrip filter technology on the front end suppresses out-of-band noise before it reaches the U-Block's MIAM10Q chip, which means the chip is processing clean signal rather than competing with the electrical environment around it. And the 18 Hz fix rate, 18 position updates per second, means that even in environments where the satellite geometry is momentarily poor, the receiver is continuously recalculating and converging back toward accuracy rather than holding a stale bad fix. The mission statement for this module is straightforward: accurate positioning even in the most signal-hostile environments on Earth. That is the physics of why your GNSS fails in cities and forests. Now let me show you the actual hardware that was designed specifically to survive those environments. This is the Multinav Pro Plus, built on the U-Block's MIAM10Q, one of the most capable GNSS chips currently available. It receives GPS, Galileo, GLONASS, and Beidou simultaneously. That multi-constellation architecture is the first line of defense against the satellite geometry collapse that destroys positioning in urban canyons. Less than 1.5 meters of accuracy, updating at 18 times per second. In an urban canyon environment where multipath is continuously shifting your apparent position, that 18 Hz fix rate means the module is constantly recalculating and averaging back toward truth rather than sitting on a stale corrupted coordinate. The full module draws 25 to 30 milliamps and fits in 26 by 22 millimeters. That compact footprint means you can integrate it into drone frames, wearable trackers, and field equipment without thermal or spatial compromises. Efficient hardware does not need to be large hardware. UART and I2C support on a single module with 1.8 and 3.3 volt compatibility. In mixed signal system designs where your microcontroller and your power rail are both negotiable, having a receiver that speaks both protocols and tolerates both voltages eliminates the level shifting and voltage regulation overhead that complicates integration. The driver library is fully open source, written in C, following the NMEA standard protocol. It imports directly into Arduino IDE or any compatible toolchain. In hostile signal environments, being able to read raw NMEA sentences and inspect fixed quality data, satellite count, HDOP, fixed type, is how you diagnose whether your position error is hardware or geometry. uCenter software lets you visualize exactly which satellites you are receiving at what signal strength from what elevation angle. If you are trying to understand why your fix degrades in a specific location, uCenter shows you the satellite geometry in real time. You can see the multipath problem happening. That visibility is how you stop guessing and start engineering. Drones, IoT nodes, wearables, automotive trackers, precision agriculture, research platforms. Anywhere that a wrong coordinate is not just inconvenient but operationally consequential. These are the environments where the difference between a filtered multi-constellation receiver and a cheap single constellation module is the difference between a system that works and one that does not. It is not a marketing position. It is a description of what the hardware was engineered to do. Every design decision in this module, the chip selection, the filter design, the antenna integration, the fix rate, exists because someone was trying to solve a real positioning problem in a real hostile environment. That someone was me, because I kept deploying location-dependent systems and watching the cheap module produce coordinates that were wrong in ways that were difficult to debug and impossible to explain to clients.
Constellations up above, locked in orbit, signal love. 18 fixes every second, every meter calculated. No drift, no guess, no hesitation, just the truth of your location. 1.5 meters from the truth, every coordinate living proof. GPS, Galileo, GLONASS aligned. Beidou locked exactly where I am. Precision at the speed of land. Fast moving platform, still it holds. Signal strength that never folds. Sky above, sky is full of signals waiting to be heard. Every satellite a compass, every fix confirmed. Nowhere on this planet falls outside the grid. 0.5 meters margin, that is all there is. 1.5 meters from the truth. Beat locked exactly where I am. Precision